In this section, we just talked about points. We could not see any sine waves. We did not see any kind of vibrations, oscillations, nothing, because we just chose a very arbitrary number, a very large one, which is fixed in very large quantities, magnitudes, and there are only 10 of them. So if let's try to manipulate this number x, this number k, and try to generate a waveform. So let's redefine k. Starting with a variable called sampling rate. Let's say I'm going to take 1,000 samples. The sampling rate is in hertz. And I'm going to generate the time axis. Earlier I was dealing with x and y axis. Now I'm going to be dealing with the time axis, which is going to be my x-axis. And I want my signal to last to start from 0 seconds and go on to 2 seconds, and in steps of the sampling rate. So that's how I'm going to generate my time in seconds. And then I'm going to specify some parameters for my oscillations. So I'm defining my amplitude as 1, my frequency as 10 hertz, and my phase as 0, because this 0 is getting multiplied by n p dot pi divided by 4. And later on we'll remove this 0 and try to simulate some phases as well. So I can use this entire data to generate k, as is seen in books which are related to communication engineering or signal processing. So we can write this as 2 into pi into frequency into time plus phase, and plug this value now in exponential function and in sinusoid function. So to generate a complex exponential signal, earlier we were using ij multiplied by k. Now this k has been replaced by this particular expression, and that's how it's going to generate frequencies with respect to time. Also, we want to double check whether the signals that are generated from complex exponential are the same as what they are in sinusoids, which is cos and sine. So we are going to use the same k, same expression of k, and now we are going to plug it in a cos function, the same value of k, and we are also going to plug it into sine function. Essentially, we are trying to verify whether this equation holds or not. And then we are going to generate the plots of both the exponential and the sinusoid and see whether they match or not. So here are the plots. Let's try to understand. So firstly, we have to appreciate the fact that the x-axis here is time, and we have simulated signal from 0 to 2 seconds, so it is correctly simulated here. The first two subplots are pertaining to the exponential, the complex exponential, and this complex exponential has two parts. One is the real part and the other is imaginary part, as you can see it from here. This is what we try to simulate. And the second two subplots are related to cos and sine. So the second plot is related to cos, and the fourth plot is related to the sine function. Now if you look closely, the real part of complex exponential is a cos wave, which is having the same phase and same frequencies as this third plot, which is coming from the cos sinusoid. That means the real part of exponential, complex exponential, is the same as the cosine waveform. It's a very big discovery. And the imaginary part of the complex exponential is a sine wave with the same phase and frequency as this fourth plot, which is coming from the sinusoid. So this confirms our Euler's formula, and this is a very, very important discovery, because what we know now is that we can generate sinusoids from an exponential, from a complex exponential, and this in turn becomes nothing but an oscillator. So let's see if it's functioning as an oscillator. So currently I have just simulated fixed frequencies here, and in fact if you want we can change them too. Let's try to change them. Let's make it 5 hertz, and you can see that the frequency has changed. In 1 second there are 1, 2, 3, 4 and 5 waveforms. Similarly sine 1, 2, 3, 4 and 5 in a 1 second interval, so it's a 5 hertz signal. We can also introduce a phase element to this. So let's say I'm going to remove the 0 phase here, and let's say pi by 2. So let's run it again, and we know that the cos when shifted by pi by 2 becomes minus sine. So this is what is the minus sine waveform, and sine when shifted by pi by 2 becomes cos. So this is the cos part of it, and exactly the same thing is happening in the exponential derived signals. The real part has become minus sine, and the imaginary part has become the cos signal. Plot 1 and 3, they are identical. Plot 2 and plot 4 are also identical. So yeah, it works. So now what do? Let's try to generate multiple frequencies for both sine and cos using the complex oscillator. So what we are going to do is we are again going to generate specify some sampling rate. We are going to generate our signal from 0 seconds to 2 seconds as per the sampling rate. And we are going to generate a frequency of 10 hertz. And this time we are going to vary this. We are going to generate 5 harmonics of this particular frequency for both sine and cos. And currently we'll just keep the phase offset as 0. So as you can see that I have initialized an array to store these harmonic signals. And then I'm going, in this for loop, I'm going from the first harmonic to the fifth harmonic. And I am multiplying that value of k with this harmonic factor. This is the only difference between the earlier equation where this harmonic factor was not there. And in this case, the harmonic has been considered. And once I generate all these harmonics, I plot them. So let's see whether this is functioning or not. There we are. So what we can see very clearly here, there are 5 harmonics of the real part, which is nothing but the cos, and there are 5 harmonics of the sine part, which is nothing but the imaginary part of the complex exponential. And by manipulating this number harmonic, we can generate multiple such frequencies. And this confirms our intuition that a complex function having imaginary part inside it, when we put a multiple called n, which is just nothing but generating harmonics, this entire function becomes oscillator. Oscillator generating multiple frequencies in sine and multiple frequencies in cos, both related harmonically. Now this is a very, very, very important discovery, and we will use this in discrete Fourier transform when we see the equations there. So that's as far as oscillators are concerned, and the theory of circle and geometry, trigonometry, and exponentials are concerned.